Hello everyone and welcome to this new video. Today we will talk about permutations as promised in the last video, and we will start by defining what permutations of a set are, and then we are going to start talking about permutation groups. Because as we will see, permutations under the operation of composition, which we can see as the classical function composition that we are all accustomed to, form a group. So they satisfy the group axioms. So let's start by defining, by just talking about what permutations are. So in essence, imagine we have a finite set, which could be of all sorts of things. It could be letters, it could be numbers. So it can be all sorts of objects, but for now, let's maybe consider letters. And well, permutations are, of course, the study of permutations is a subset of the branch of mathematics that is known as combinatoric, which fundamentally solves the following type of problems. It is problems of rearrangements of sets, usually finite sets. In fact, it is often covered in discrete mathematics courses. It aims to find techniques that allow us to, we could say, rearrange the structure of a set without actually changing it. Now, what we said really doesn't make that much sense as of now, because we really didn't define in any way what we mean by without changing it, and also we didn't define what sort of structure or ordering are we even talking about. In fact, when we could say when we have a series of elements, we have a set, and then we start talking about some extra structure, we always have to introduce that extra structure. That is in fact what we actually did at the beginning of this series when we start talking about algebraic structures. So in fact, what abstract algebra really is just taking sets and building an algebraic superstructure on top of it via, well, we could say n-ary operations that satisfy certain axioms. So we have a set, and then we have n-ary operations that we can call phi of n, and this phi of n then might satisfy many. We could have more than one actually, and these n-ary operations might satisfy some we could say collection of axioms, and we then classify them and prove theorems about them. So we're interested in this field here. We're interested about the algebraic superstructure built on top of a structure of a set. What about combinatorics? With combinatorics, we are interested in studying sets, and then actually we could say this superstructure we build on top of it, with which we then can ask questions about rearrangement. One of the simplest, in one of the simplest cases, this is concerned with, so permutations of a set, which are just the possible rearrangements of a set like this. One such a rearrangement could be the following, and another rearrangement could be the following, for example, and so on. And so, well, in the same way, many other areas of mathematics do the same. Topology is nothing but having a set and giving it the notion of nearness, so that we can start talking about the concept of nearness, which is also, and really there's many other examples of this, but we will stop here. And well, now that we have a little bit explained what we mean by this, well, the notion of ordering and reordering of sets, let's now define what we mean by keeping a set the same. So we already understood that our goal is, well, as an input, imagine we have a set. Now let's denote it with numbers, so 1, 2, and 3 maybe. And our goal is to take this set and find all possible rearrangements of the elements. So where we consider an ordering. So we actually, this time we care about what comes first and what after. So for example, one such example could be 3, 2, 1, then 1, 3, 2, and so on and so forth. But our goal is to study this in a rational manner, so in a way that it is actually scalable, we could say. And well, how can we do this? So the first thing that we can do is to understand this shifting as a function. So we can say a function sigma, which maps an element of A to an element of A. So we can imagine shifting elements as just saying taking the element with the original ordering, which is this one here, and then saying where the image of any element of A with respect to this mapping that we call sigma, which is still an element of A, we represent the new element that will occupy the place that X formerly occupied. So with this, we could say notational introduction. So with this notation that we introduced like this, we now have at least the theoretical understanding of these rearrangements as functions. But now we ask, is there some other things that these mappings need to satisfy? In other words, about our intuitive understanding of the nature of a rearrangement, is there any other abstract condition that we should make sure these mappings satisfied? And well, the answer is yes. We intuitively said at the beginning that we would like to have that these rearrangements of our original set would keep the set unchanged. What do we mean by that? So if we have a set such as 1, 2, and 3 as before, to rearrange the elements, we would ideally like that, well, no element was lost in the process, for example, because imagine if we rearranged them and we didn't have 3 anymore, or we had another element that wasn't there at the beginning or something like that, or we had another extra element. And so, of course, if we mean rearranging the elements of a set, we mean switching the positions of precisely the same amount of elements, and in particular, switching the position of the same exact elements. So this brings us to defining a permutation as also as a function, sigma from A to itself, that is also injective. That is, that given, we could say y and y prime in A, such that sigma of x is equal to y and sigma of x prime is equal to y prime, then this implies that x is equal to x prime. And surjective. That means that for all y in A, there exists an x in A such that sigma of x is equal to y. Two conditions together, which is a function which is injective and surjective, is also called bijective. So we require sigma to be a bijection. And actually, and going back to what we were saying earlier, so to keep the set the same, a bijection of a set is precisely this. Basically what we could say, and this is out of the scope of the video for now, of course, in a category theory, it is an isomorphism in the category of sets. And here we need to be a little bit careful when we talk about category of sets because of axiomatic reasons. But for now, let's not go into that. Let's just know that an isomorphism for sets is a bijection because a bijection keeps the structure of a set the same. A couple of videos from now, we will also introduce the notion of isomorphism for groups, which is pretty much the same thing, except that, remember here we said that when we study abstract algebra, we give some algebraic superstructure on top of our sets. And thus, we will have to take for other things into account in order to speak about well, equality in the context of groups. So, of course, an isomorphism for groups fundamentally does the same. It keeps the group structure the same. And so when we will talk about isomorphic groups, we will talk about groups which are, in terms of algebra, in terms of their algebraic properties, the same. So with this said, we now have the notion of a permutation. Let's now give some examples. So for example, if we have a set 1, 2, 3 that we can call A, then we can ask, well, for example, we can give some examples of permutations. So one such permutation could be 2, 3, 1, where here we mapped 1 to 2, 2 to 3, and 3 to 1. So, and well, from this explicit expression of our sigma, we can here immediately check that this is a bijection. And so this is one example of a permutation. Another example of a permutation could be 3, 1, 2. Where in this second permutation that we can call sigma 2 of 1 was mapped to 3, and similarly this. So these are two examples of a permutation. But now we might ask, how many permutations are there in general? So how many ways to rearrange this? How many ways to rearrange the order of an original set are there? Well, we can brute force this for now, then we will kind of try to see a pattern and maybe prove a general result. Well, we can see that we have 1, 2, 3, then 1, 3, 2, then 3, 2, 1, and then 2, 1, 3, which in total is 6. which is equal to 3 factorial. And now we might ask, is this a coincidence or is it a general result? It turns out it is a general result, and I'm sure maybe you have already heard of it because it is usually already covered way before an introduction to group theory. But however, before we actually prove this fact, let's first state some important postulates, which are known as the product rule and the addition rule. And the addition rule says that if an element needs to be chosen from one of n disjoint sets, and notice here that we mean pairwise disjoint sets, meaning that we have n sets such that they're all disjoint for any indices which are different from one another. And each one contains mi elements, meaning the first set will contain, actually here m1 elements, then the second one m2, and so on. Then there are in total m1 plus m2 plus mn choices in total. And here I've used the sum notation here to write it more compactly. And the second postulate that we will accept is the product rule. And that says that if there are n consecutive choices to be made, then supposing that for the first choice we have m1 possibilities, and then for all the other ones we have mk possibilities. What do we mean by that? We mean that for the second choice we have m2 possibilities, for the third one we have m3 possibilities, and so on. And we're supposing here that, of course, the number of possibilities does not change. In other words, it is not impacted by the choices we made before. Then the total number of possibilities is the following. In other words, it's the product of all the possibilities. In m1, m2, up to mn. And then you might ask, how do we prove the assertion that we made before about the number of permutations of a finite set? Well, the proof is very simple using the product rule. And so let's here state the theorem. And that is, if A is a set with cardinality n, then there are n factorial permutations of A. And we will actually prove a result that is a little more general than this, and that is there are n factorial bijections from A to itself. So bijection phi from A to A. So let's prove it. So let's see that, let's call our set A as A1, A2, up to AN. So that's n elements. In other words, that's order n. Let's suppose that phi is a bijection from A to A. Then phi, in order to be a bijection, needs to, of course, since it is a function, it maps each one of the elements of the domain, each one of the elements of A, to one and only one element of A. And since it is surjective, all the elements of A get paired to one element of A. And since it is injective, two elements of the codomain cannot be quote-unquote used twice. So, in other words, we will find the number of bijections, we could say, inductively. So, let's start by picking one element of A, and that is by considering phi of A1. Then, how many choices do we have? So, how many elements of A can we put phi of A1 equal to? Well, AI, where I is in between n and 1, not strictly. Okay, so we have n choices. Okay, but remember, this is a bijection, so it is surjective and injective. We do not want to take the same element again, because then we would lose injectivity. And so what do we do for the second element? We have how many choices? Well, we have, again, we can map it to an element AI, of the form AI, where I is in between n and 1, but notice here that I needs to be, actually let's call this J, or actually I2, this is I1. But notice I2 needs to be different from I1. And for the same way, A3, we have A of I3. I3 is between 1 and n, and I3 is different, so it's not equal to I1 and I2. So how many choices did we have for phi of A2? N minus 1 choices, and here n minus 2, and so on. So in other words, to build a bijection, and we continue this until we exhaust the elements. In other words, until we have covered all the set A in order for our function phi to be surjective. And so in total, at the end, the number of bijections by the product rule is just n times n minus 1 times n minus 2, until we exhaust the number of elements of A. So we end with 1, and this is just n factorial. And this proves the fact. Okay, so now that we know what permutations are, and we have worked a little bit with them, let's now introduce a little bit of notation. So let A be a set as before. Then we can call A1, A2, up to AN with cardinality equal to n. Then we will call an element of the permutation of the set of all permutations that from now on we will denote as SA, all permutations of A. We will start to denote it as the following sort of array notation, we could call it. And basically we will put the array in the original ordering on the top, and then on the bottom the image of each one of the elements of the original ordering. So for example, in the example that we gave above, that is this permutation here, let's call this permutation sigma here, and from the old example, then that would be 1, 2, 3, and then on the bottom we will have 2, 3, 1. So this is an example of how we will use this notation. And one might ask, well, why is this notation useful, and why is it beneficial at all? Well, because with this notation it is more explicit what element gets sent to what other element. And not only that, but recall that permutations are functions. And being functions, they can of course be composed with one another. So if we have two permutations from SA, then of course we can talk about their composition. And the fact that this is still going to be a bijection from A to A, we will see it in a more rigorous proof later. But for now, just know that we will also be interested in composing permutations together. And you can immediately understand why this notation can be useful to multiply. So we will use the word multiply, but we really mean composing permutations, because well, imagine we're composing two permutations that we call sigma, and so we have as before, and then another permutation mu, which is going to be A1 mu A1, A2 mu A2, AN mu of AN. And so taking sigma composed with mu will basically be equal to, we will denote it as this product here, and then the multiplication just boils down to applying this permutation here first, and then applying this one. So for example, imagine we want to see where A1 goes under this composition. Well, then we see where A1 goes first, and we see that A1 goes to mu of A1. Then we go inside here, we see where mu of A1 is in this, and maybe it is here of mu, sends A1 to this element here. So it also gives a pretty graphic way to multiply together permutations. So now that we have mentioned actually compositions of permutations, we wish to see if under this operation the set of all permutations of a set is actually a group. And this is actually the case. And also it's not only true for finite sets, which are the sets that we have considered so far, such as A, but it's also in general true for a set X. So let's state it as a theorem. And that is, let X be an empty set, and we pose no restriction on the cardinality of X. And well, then let Sx be the set of bijections phi from X to X, and then Sx under function composition is a group. So let's prove it. So we won't check associativity because we know already that function composition is associative, so we won't prove it directly. Well, now let's look at the second point, which is closure. And well, for closure, suppose we have two permutations inside our sets of permutation, which is sigma and mu, and let's suppose we compose them. So, and we know that sigma and mu are bijections from x to x. Well then, if we consider sigma composed with mu, we want to show that this is a bijection. So let's first show that it's surjective. Let's suppose z is an element of x. Then, since sigma is bijective, there exists a y in x, such that sigma of y is equal to z. But now, since also mu is bijective, there exists a x in x, such that y is equal to mu of x. In other words, for all z in x, we have found that there exists an x in x, such that sigma of mu of x is equal to z. In other words, sigma composed with mu is surjective. So we have proven that the function is surjective. But what about its injectivity? So let's suppose that sigma of mu of x is equal to sigma of mu of x tilde. Well then, since sigma is injective, we have that mu of x is equal to mu of x tilde. And since mu is also injective, we get that x is equal to x tilde. So in other words, sigma composed with mu is bijective. And so with this, we have proven that given two permutations, then also their product, so their composition, is a permutation. So in other words, the operation is closed. Now let's prove that there is an identity. Yes, we assert that the following function, which we will call ID, that goes from x to x, such that for all x in x, ID of x is equal to x, is the identity of this group. So for the first thing, let's prove that ID is actually a bijection, but this is trivial because, well, for surjectivity, for all elements of x that we could call y, then there exists an element x of x such that ID of x is equal to y, and that is precisely y. And for the injectivity, this also follows trivially from the very definition of the function, because if we have that the arguments of two functions are equal, since the function is equal to its argument, then we will have that the arguments will coincide. So the function is a bijection, and thus ID is an element of S of x. But to prove that this is actually a identity, let's look at the composition of ID, both on the left and on the right, with any permutation that we can call sigma. So for the first composition, since ID of x by definition is equal to x, this is going to be equal to sigma of x. So in other words, sigma composed with ID is sigma. For the second composition, on the other hand, since ID of any element of x and sigma of x is an element of x is equal to itself, then we will have that this is equal to sigma of x, which implies that ID composed with sigma is equal to sigma. So in other words, these two are equal, and these equations give that ID is the identity. And now for the last thing, we have to prove the existence of inverses. So in other words, for any, we want to find an element, so for any sigma in S of x, an element sigma to the minus 1 inside of S of x, such that sigma composed with sigma to the minus 1 sigma is equal to sigma to the minus 1 composed with sigma, and it should be equal to the identity. So how can we do this? Well, we're going to call our sigma to the minus 1. We're going to still require that this is a function from x to x. We're going to define it in the following way. So we're going to say that sigma to the minus 1 of b is going to be equal to a if and only if sigma of a is going to be equal to b for a and b in x. Okay, but now in order to prove that this is actually an inverse, we first have to show that sigma of the minus 1 is actually an element of S of x. Also, we have to show that then that the product of this function with sigma yields the identity. So let's first prove that sigma to the minus 1 is actually an element of S of x. So for the first point, we're going to prove them together, which is the injectivity and well-definedness. So let's suppose that a is equal to b in x. Well, then let's consider sigma to the minus 1 of a and sigma to the minus 1 of b. Then sigma to the minus 1 of A, we're gonna say it's equal to A tilde, and sigma to the minus 1 of B is gonna be equal to B tilde. Okay, but this is the same thing as saying that sigma of A tilde is equal to A, and this is the same thing as saying that sigma to the B tilde is equal to B. Okay, but A and B are equal by hypothesis, and so we have that sigma of A tilde is going to be equal to sigma of B tilde, and so we have that A tilde is going to be equal to B tilde, and this implies well-definedness. So now, on the other hand, we're going to suppose for injectivity, we're going to suppose that we have another elements C and D in X, and we're going to have sigma to the minus 1 of C is going to be equal to sigma to the minus 1 of D. Okay, but sigma to the minus 1 of C, we're going to call it maybe C tilde, and this D tilde is the same thing as saying that sigma of C tilde is equal to C, and this is the same thing as saying that sigma of D tilde is going to be equal to D. But since we have that C tilde and D tilde are, but since we have that by hypothesis that C tilde and D tilde are equal, then we're going to have that also C and D are going to be equal by the properties of the permutation sigma. Well, why? Because sigma being a function is well defined, and so we have this. And now, as a last property, we have to check for surjectiveness. So suppose we have an element y in X. Well, then we know that sigma is surjective, so there exists an X in X, such that sigma of X is going to be equal to y. But what about sigma to the minus 1? Okay, but now we can prove this pretty simply following using the properties of sigma, because considering an element that we can call y tilde inside of X, then we want to find an X tilde in X such that sigma to the minus 1 of X tilde is going to be equal to y tilde. But notice that this X tilde exists and it's precisely equal to sigma of y tilde. And from this we have proven that sigma to the minus 1 that we have defined in this way is actually an element of S of X. But now let's prove that sigma composed with sigma to the minus 1 is actually the identity. And I won't show that also sigma to the minus 1 composed with sigma is the identity because it's a very similar calculation. But let's see. So let's apply sigma to the minus 1 of X. Okay, but we have said that sigma to the minus 1 of X is going to be equal to B if and only if sigma of B is equal to X. But now this is precisely B, and so all of this is just X. And so from this we have proven that this equality is true, and so we have shown that S of X under function composition is a group, and which gets its motivation from the preceding theorem, and that is the symmetric group. So we will define this for finite sets, and so we're gonna call let A be a set, a finite set of order n, or of cardinality n, a1, a2, dot, dot, up to an. Then we call the group of its permutations the symmetric group of degree n, and we denote it like this, S of n, or sometimes S of A, but we will show that when we study permutations, it really we don't care if we have n elements, and these elements are actually represented by numbers, or they're represented by like elements with indices, with sub-indices that are natural numbers. So we're just gonna stick with the notation S of n. From the facts that we have derived above, we now know that S of n is a group, and in particular it's a finite group of order n factorial. Okay, so with this said, I think we have covered enough in this video, and in the next video we're gonna prove some other important facts about permutations and also some other facts about the symmetric group.